So now let's talk vector products. Okay, these are also called cross products by the notation because you got vector A cross product vector B. Okay, when do we use this? This is how we describe torque and angular momentum. Okay. So a lot of physical quantities can be described by the dot product. So we've got dot product of A, or cross product of A and B gives us some vector C. Now, the magnitude of C is equivalent to AB sine of phi. Again, you start out tails together, and it is the magnitude of A times the magnitude of B sine of phi. Okay? Now, phi should always be in between 0 and 120 degrees. You use the shorter angle in between vector A and vector B. Now, vector C, this is what's different. Vector C is always perpendicular to the plane A and B occupy. Okay? Now, what do I mean by that? Say I've got vector B, it's running along the screen. Vector A, let's say it's coming out of the screen. Okay? Well, their angle between, we're going from A to B, the cross product of A and B. The angle between, you'll see, is kind of going like this. So what we do is we use the right-hand rule. Okay? The right-hand rule, how that works, is you take your fingertips and you curl it with the movement going with the arrow of their angles. Okay? Your fingertips point in the same direction as the rotation of A to B. Okay, so I'm curling my right-hand fingertips from A to B. Well, your right thumb tells you the direction of C. In this case, it's pointing straight up. So that is how you find the direction of C, using the right-hand rule. Now, you can also find the components of C by couple different ways. Okay, what we're going to do is we're going to use 3x3 matrix, and we're going to use its determinant. Okay, so components of C, we got Cx. I'm just going to give you guys the definitions now. Cx is equivalent to Ay times Bz minus Az times By. Cy is equivalent to Az times Bx minus Ax times Bz. And lastly, Cz is given as Ax times By minus Ay times Bx. So how we're going to use a matrix, okay, is we're going to first draw a 3x3 matrix, and we're going to use our unit vectors. So we've got I hat, J, and K. Okay, so from there, we're going to fill in, we're going to go Ax, Ay, and Az, and then we're going to go Bx, By, and Bz. Okay? And we're going to write out the determinant of this matrix. Now, finding a 3x3 determinant, just a little refresher, how you start is, in a sense, you copy and paste the first two columns to the right side of the matrix. So just like they're written, AX, BX, and then J hat, AY, and BY. Now, what we're going to do is we're going to go left to right. So we're going to go this diagonal, and then we're going to go this diagonal, and then we're going to go this diagonal. So we get AY, BZ, I hat, plus, we're going to add these together, and then we're going to add the green diagonal. So we've got AZ, BX, J hat, and then we're going to add our third diagonal. So plus, we've got AX, BY, K hat. Now, from this, we are going to subtract going from right to left. So we're going to subtract this diagonal. We're going to subtract this diagonal. And we're also going to subtract this diagonal. So, starting with the top right. I guess I should have done that one in green since it's a J, but we can figure it out. We've got AX, BZ, J hat, and then minus AZ, BY, I hat, and then minus, my K stayed true, stayed pink and true, minus AY, BX, K hat. And just like before, we're going to group our like terms and factor out our I hats and whatnot. So as you can see, our vector C is given as I hat, AY, BZ, minus AZ, BY, and then plus J hat. We've got AZ, BX, minus AX, BZ, plus K hat, and that is AX, BY, minus AY, BX. So, just like up here, but we used a matrix to figure out our components. So instead of having this memorized, we used a matrix. We could plug in our components and figure out the components of C. So let's do an example where we are actually finding a vector product. So let's say we've got vector A has a magnitude of 6 units, and it points in the positive x-axis. And vector B has a magnitude of 4 units, and it lies 30 degrees above the x-axis. Okay, so if we think about this, let's draw an xy coordinate plane here. So vector A has a magnitude of 6, so it's right along this x-axis. And then vector B, let's go green. Vector B has a magnitude of 4, and it lies 30 degrees above the x-axis. So it's 30 degrees right here. Okay, so let's use the right-hand rule and figure out where C is going to point. If we curl our right hand fingertips from A to B, so we're curling our right fingertips just like this around, your thumb should be pointing right back to you. In other words, it's coming off the screen. So Z is coming out of the screen, and Z and C are pointing right along that axis. So vector C is coming right off the screen, out towards you. So to figure out the magnitude of C, we'll remember that it is AB sine phi. And that equals 12 units. Now, our components. We've got AX equal to 6, AY equal to 0, and AZ is also equal to 0. BX is 4 cosine of 30 degrees. BY is 4 sine of 30 degrees. And BZ equals 0. So, if we use a matrix to figure out our components of C, we've got our I hat, J hat, K hat. Let me shimmy this down a little bit. So, AX goes here. We got 6, 0, 0. BX goes here. So, 4 cosine of 30 gives us 2 square root 3. 4 sine of 30 gives us 2. And our BZ component was 0. So, if you do the determinant and you combine like terms, you get CX equals 0. CY also equals 0. You only have a CZ component, which is 12, the same as our magnitude, which makes sense because C lies on the Z axis, coming right out of the screen towards you. And that there, my friends, is vector products and scalar products with a little bit of unit vector review.